Hi, this is Sean Murphy of SK Murphy. I want to welcome you to the PACTA webinar on service deployment of ML models. Aakash Gupta brings a rich set of experiences building and managing data science teams to this briefing. He's a data science consultant at ThinkEvolve. He enables startups to leverage the power of their data and AI models. Prior to starting ThinkEvolve, he was the VP of Data Science at Edelweiss in Mumbai. He has also worked in senior roles in banking, financial services, and insurance. He has an MBA from the Indian Institute of Management in Indore. He's a Kaggle Award winner, as well as multiple hackathons, and he's an open source advocate. Aakash, welcome.
So this talk is about serverless deployment of ML models. And what I'll do is that I think it is a very short talk, about 20-30 minutes. But if any one of you wants to butt in and ask me a question, I'll be happy to answer those questions. Right. And I will also showcase a demo that we have created for this talk, which might give you some flavor of what serverless deployment means. So as Sean has given me an introduction, so I will not talk about myself. I'll just talk about a company, which is ThinkEvolve Consultancy LLP, which we have just started about a year back, and we help startups and enterprises with their data problems. We are more IP focused as such, and that we're trying to, we have filed some patents in the US and trying to publish in conferences. And we are mostly working with health tech and fintech companies based out of North America and Europe. So let's try to look at this from a perspective that this is a general thing that, as Carl said, that AI is like, if you look at the popular media, you'll see that AI is everywhere. From driving cars to finding something as finding superbugs and finding vaccines, or running these kind of beautiful robots out there. There are a lot of use cases that we see out there, and like some of the use cases that like my team works on is like having people count the people in the crowd, creating 3D representations, or creating generative art. Some of the papers that we have submitted is on generative text material. So, but these models, they are generally very heavy in size. Heavy in size in that sense that they take a lot of space. So if you look at transformer models like GPT-2, they are about 500 MB in size. GPT-Neo, which is the open source version for GPT-3, is 10 GB in size. Similarly, T5 base, which is, yes, Carl. You are muted. You're muted.
Oh, yes, I'm sorry. Yeah, you might explain what a language transformer is, and then go on.
Okay, cool. Cool. I'll take a step back again there. So the language transformers are basically a large set of matrices which help the model understand the language. So for us, language is English words and alphabets. For Latin is some kind of, you were talking about Latin, taking Latin classes and Italian classes. Those are a set of words which together, there are phonetics in there, there are phonemes of there, which together make us understand it. But for a machine or a model, you need to make a transformation so that a machine can understand. Now, how do they understand all this thing is because they have been trained on large corpus of text data. So we had GPT-2 some years back where OpenAI, there's a community called OpenAI, which trained large corpus and created a model so that you can easily use it for any other task. So they are pre-trained models which are trained on large textual data, and then you can reuse them for your specific requirement. Now GPT-2 and GPT-3, there was a third version out of it, and those are closed sources, like they didn't open source the entire weights and everything. So someone tried to recreate their efforts, and that is GPT-Neo. And as you can see, the size is 10 GB. Similarly, Google has opened their largest model that they have open sourced is T5 base, which is around 850 MB in size. And similar to language transformers, you have vision models and audio models, and all of them are large in size. Now, for running these large models, you require specialized hardware called GPUs, basically because machine learning is basically a lot of matrices matrix calculations taking place. Now, when you do that, you require GPUs, which is hardware, and you need to run them. And typical cost for GPUs for running such high-end models could vary between $2,000 to $5,000 a month. And this is considering the entire architecture that you are setting up a GPU server for inferencing, right? So if you have such this model, you have to run it. You need a infrastructure. You need some kind of engineering talent to maintain those servers, and you have storage cost. To the left of the slide, what you see is a snapshot that I've taken from a GCP cost estimator. It's a relevant cost which I've taken, but like you can of course shop around for more cheaper GPUs. You could look at okay, I don't want to maintain this amount of latency. I can have a smaller GPU over there, or I could like maybe not take care of too much of traffic coming up. But these are like a kind of a sunk cost that you have to maintain your business to give that kind of an innovative solution to your customers, right? So,
can I ask a quick question? When you
say
sure, yeah, when you say that GPT has 10 gigabyte size, what does that mean? Is that the size of the data that it can process? So
it's the size of the model weight. Okay. And 10 GB is for GPT Neo, which is the open source variant. So that is the size of the model weight, which needs to be on the GPU for making any kind of prediction or inference.
So it's a metric of computational
weights.
Yeah, needs. Okay.
Yeah.
All right.
Yes. So I will like try to bring this in perspective from the entire model development lifecycle that takes place, right? So what you see here is the entire like the life cycle of a machine learning process, which always starts when the business has a certain problem statement, which we can convert to a data problem, right? Once we convert that to a data, we try to create different, get the different type of data which we can use. If you would take the training data and we take a training code and try to build models which might give you the required results, right? So in the model building process, we'll not create only a single model, we'll create some candidate models, about 5, 10, 15 different types of models to see how the different model architectures work for a particular use case, right? And once those model architectures are ready, we will then evaluate them on a set metrics. Maybe the metrics is accuracy, maybe it is F1 score or any other RMSE score, whatever accuracy you feel like, evaluation metric that you want. And once that is done, from those candidate models, a few of the models are chosen and then they are productionized, right? We put it into a production environment. And therefore putting in a production environment, always you'll test it with the inference code because you want to ensure that proper pre-processing of the data is taking place, the inference is taking place, and then the proper post-processing is done so that the information reaches back to the business user. And finally is a deployment stage where the model is finally deployed into a production environment, right? And this is where we are going to focus our attention. And of course, later on, this is the monitoring and observability because we want to ensure that the model is actually performing as per our requirement and there is no data drifts or model drifts taking place. So that takes place. So for this entire life cycle, we have a number of tools that have come into place, right? This is like machine learning, I think is a lot of, there's a lot of things in a growth kind of phase, like things are maturing out there. So for model, you have some things like auto ML, you have ML ops, right? MLOps, you have feature stores. Those are different, and those are components in this development cycle. For say for monitoring observed, you had tensor boards, weights and biases. Those are tools that can be used for it, right? And they are helping it, the entire life cycle, to improve and become more efficient. And so we look at how we can make this part, this component, more efficient, and like ensure that, because whenever I start with any model development, I always look at where the model is going to be deployed. So that helps us determine this entire process, because then if you know where it's going to be deployed, then our model building will also change depending upon, and we'll select the specific architecture as per that. Anyone has a question on this? Good.
So the life cycle, so the life cycle for a model is very different from the life cycle for a regular kind of algorithmic software, right? When you talk about ML ops, that you're drawing an analogy to DevOps, but this life cycle is a different process from a normal software development, or the software development cycle, I think, that we're used to. Are you going to cover how the serverless deployment then looks different from a regular ML deployment?
I didn't have that. I don't think.
Okay.
We'll cover it. We'll cover it, Sean, in the course of this presentation. Okay. So yeah, one step at a time, actually.
This is a beautiful slide. That's a good slide.
Yeah, it's been. I actually didn't write a source out there, but it's a very good one. So yeah, this is the inference architecture. It's nothing more than your business requirement being converted to code, right? A data representation, which being used to make a prediction by the model, and output being again converted to a business decision, so that person can make a proper response of that. So yeah, so we come to a demo link. I'll stop sharing this link and I'll share my second screen. So I hope you can see that at your end.
Yeah, looks good.
Looks good. Okay, cool. Cool. So this is a small demo that we made. This is basically here the model is running on my browser screen instead of running at the backend on a server. And this is very useful when you do some kind of real-time processing. And it's useful. So for example, so what it does is it picks up my video from my it picks up the image from my model and tries to segment each pixel into different classes. So, and those classes are written out here. So this it's basically observing me to be a person out here. So that's a pink color. Behind me, there's a TV which comes in and goes, and then so that's in blue in color. So I'll just try to show you some more examples, because we are, like say I'm showing here a horse. So as you can see, it has identified the area, the pixels that define the horse, and the color it's shown out here. So this is an example of how we can, another example, we can use it. There's an example, another example of a train. So if you see this red color being green color coming from there, right? So this model actually is only 15 MB in size, whatever you see out here. And it works pretty much on, it can work on anyone's, without placing any kind of a requirement for the user to add any, what we call as any packages or anything. It can pretty much do the work for us.
But, Aakash, where is the training data stored, on the cloud or on your laptop? Or
this is are you talking about a model? Where's
Yeah,
the
it's
model stored?
obviously it's recognizing the image
Yes.
due to some training, right?
Yes.
And
Yes.
that training is stored somewhere.
The training data, the model is stored. Model is actually
It incorporates the training.
yeah, the model incorporates the entire training.
Okay.
And when I open this browser, the model is downloaded onto your machine, onto your browser, and it does the inference on the browser. So if I disconnect, like this machine gets disconnected from the internet, it still will be doing that inference.
Right.
So you understand that this is very important because it's very privacy friendly.
Yeah.
Things,
so it has loaded the model instance onto your computer and it's doing everything from there on.
It's doing everything, and since the model has learned all those abstractions for detecting these 30 classes, it can do well for those 30 classes, and it can do for multiple classes also. So that's the idea.
So just to clarify, what you're showing is the equivalent of an on-premise production model running in the browser. So if I had paid for that model or whatever, subscribed to it, the vendor wouldn't have access to my data. I would be running their production model locally, in this case, locally in the browser. So from a personally identifying information point of view or confidential information point of view, this is very privacy friendly.
Yes. It's privacy friendly, as well as a lot of things is like the person may not have that kind of a hardware to run it. There might be other constraints out there which get tackled because we are just placing it on a browser, and the small size of it makes it even more interesting. So I'll just maybe stop this. Yeah, I stopped it. Cool. So I have shared a link in the chat. You can try it maybe after this session gets over. So you can copy it and just check it out and check if those things are actually working or not. I've just shown. Right? So
do you think this is part of a larger trend to move the program to the data instead of the data to the program?
Yes. It's more of a distributed nature where like things like I don't know, maybe like things go centralized and then they start becoming decentralized in a sense. So in a distributed sense, maybe.
So the only challenge of this, I think, which Lester was hinting at, is that in terms of developing the training model or developing the richer model that you then simplify for production, that wouldn't work because that model is going to be much bigger than the compact production model, right?
Correct. So I will cover those things in the next few slides. I have that thing, and I have that in the agenda out here.
Just a quick comment on the relevance, because in the industrial space, it's this whole business of computing at the edge versus computing in the cloud is becoming important because of this cost element. So there's always a decision as to how much data do we start processing at the edge, on premises or at the edge of a cluster versus loading it up into some central gargantuan cloud and then waiting for it to come back. So that's a big challenge, the edge versus cloud, and it's, this kind of demonstrates that effect.
Having it at the edge helps you make fast decisions. You don't want to spend time waiting for the response coming from a central server.
Right. Plus the expense.
If you were in a car, for example, that was relying on AI to drive, you wouldn't want it to stop working if it lost connectivity with, the cloud, speaking hypothetically.
Yeah, that's right. And from privacy perspective, let's say if you are monitoring inside the vehicle for, let's say, driver's fatigue detection or something like that, you don't want people's faces to be streamed to a server that they don't have any they don't have any knowledge about. So it's more from privacy perspective, people try to avoid sending their personal data on cloud. And that's why most of the industry we see, most of the models are getting deployed on edge side.
So yeah, as you see, the models, there's a reason for this need. It's called model being optimized, because you're optimizing it for that particular environment. And the reason could be that you cannot host, as I said, large models. You can't host large 10 GB, 500 GB models on a CPU. It simply slows it down. Okay. So, and you may not have even the large disk space on an IoT device. So you need to reduce the size of the model. That's called as optimization. There's a latency factor. The latency is important in a number of cases. Self-driving cars, for instance, you cannot have latency. The decision has to be made at that place, right? Then there are other resource constraints like bandwidth not being available. That's the internet bandwidth not being available. No signals in a lot of places. A lot of places in rural India, or in, say, something as a warehouse or containers, they don't have a good network. So you can't wait for them for the API to make a central call and then get a response back. So those are some of the reasons where we can't. And of course, the privacy case is one more thing that we looked at. And so what are the ways you could do serverless deployment, right? SAM is one of the processes that we are using, which is basically AWS open source approach or a framework. It's known as serverless application model. And what it does, it provides us shorthand syntax to express functions, APIs, databases, and even source mapping. And with very few lines of code, we could just create an entire pipeline and entire application using YAML. And you can deploy them easily using CloudFormation, AWS CloudFormation, that is. The second is the browser side, which is on the client side, just as we saw the demo out there. Here, the entire model is on your web page. Once it gets loaded, it will continue to do the inference. Another good point here is the client doesn't need to install any packages for it. So it's all self-contained on the web page itself. And as a developer, I just need to host that web page on my website, on my server, and which is pretty cheaper. And of course, the most important thing, it's privacy first. Data is with the client. It's not going back to the client server. Another option is Android. I think everyone has Android or iOS. Everyone has a mobile application, a smartphone application. I believe in India, about 1 billion mobile phones, smart mobile phones are available, which is a big, huge number. The penetration is huge. And the only problem here is that you need to tweak your models, tweak the application for each individual cases. So you need to test it as well, because it needs to be portable for an Android device, iOS device, within Android, within different OS version, iOS version. So for that, you need to make changes. Sometimes some hardware is not, there are hardware incompatibilities, and some programs work in some place, it doesn't work in other places. Then, of course, there are IoT and edge devices. Lester has made a very interesting example of that. We want models to be on edge because they cannot have that latency. So you have smart web cameras which can do that kind of check the image and make a judgment call out there. And if there's an emergency, they can make a call. There are smart, what do we call them, as portable heart rate monitors, which patients can wear, and with a single ECG lead, they can identify if there's a atrial fibrillation taking place, and they can call their health providers. Another thing is now these maybe it's a little like satellites are easy to be, you can easily build and deploy a satellite at around $500,000. But if you look at a drone, it gives you the same power and the same and with greater flexibility. So with a drone, you can models deployed on the edge can do better inference with proper infrared cameras kept out there and with embedded on those devices. So I'll take you through two use cases, which are real life.
One question: are you assuming that you're using the NVIDIA GPU for the most part?
NVIDIA GPU, yes, I'm assuming NVIDIA GPUs.
Okay. So those don't tend to be battery powered then. So there isn't really a power. It's more about bandwidth and latency. It's not, this is not necessarily a low power option as much as it is a faster response, the faster response and the privacy.
Right. But there is also the case is that if you can run a model like a computer vision model, you can run on a GPU, it will, and you can run the same model on a CPU instance also.
So could you run on like a Raspberry Pi or something like that?
Yes, you could do that. You could do that, but then it will take such a long of time because it's computing. It may take 10 minutes, 10 minutes out there.
Right.
Right. So the latency factor is coming in. And yeah, NVIDIA. So yeah, microcontrollers, one of the Jetsons, you have Jetsons out there, which can, Raspberry Pi, which can help you productionize things faster. So yeah. I just thought I'll talk about this use case. It's a marine insurance company and it's UK based. They do quality audits for transit insurance. They enable remote containerized cargo inspection and claim resolution faster. And how do they do it is that they use AI/ML for that. And one of those things is that what they did was they created an object detection model using YOLO v5. And they deployed it as a web app. Because they didn't want to spend, like, it's being resource constrained. As bootstrappers, we are resource constrained. And web app does most of the work. Why do you need to build a mobile app, right? So if you do a web app, the problem is this is a very resource constrained environment. You are in a warehouse or a container ship, and you're trying to take an image of those boxes, right? And when you do that, you don't have any bandwidth where you can call the API endpoint. So that's where that becomes a very good use case for having something like a browser-based detection model. And this works very, very beautifully out there. And you don't need any connection. You can have the inference take place, all the logic built in out there. And once the person who's taking the audit comes back to the show, outside into a better environment, he can simply connect to the central servers and give back that information. So this was a very interesting use case. Another use case is a US-based health tech firm. They tried to, they wanted to identify certain data from an imagery, medical imagery, and they had built a pipeline using AWS recognition. But then they learned that their POC was not working as per their requirement. So we did some research and we identified that the reason it was not working was because the models were not trained on that specific type of data. So we trained an entire model for them and deployed that as a lambda function, right? So normally these object detection models are 250 MB in size, but we use a technique called quantized adaptable training, quantization aware training, that is QAT, right? Quantization aware training, which ensures that the model it's about like 1/10 of the size. Being 1/10 of the size, I can actually deploy them as a lambda function. The advantage being that it becomes completely serverless. I use the SAM open source framework for this. I set up the system, put it on ECR, X-Street model weights, and run it as a lambda function. top up to that, having done is that AWS Lambda gives about 1 million requests and 400,000 gigabit compute time per month free of cost. So for the user, there is no running cost of a GPU, running a GPU server, setting up a Kubernetes cluster or KFS. They don't need to do all that. Okay, they just need a Lambda function. There's an API call, a change, even the API call in their front end, and it makes a call, gets back a response, and it saves cost. So that improves your ROI on the project. So yeah. So in this, all the talk that we had, we spoke about model optimization, quantization. So we'll spend next few slides. If anyone has a question before I move to the next slide, they can ask me, because next might be a little more technical in the sense. Good. So you can quantize a model in two ways. You can do before the training, or you can do after training the model. So you can train your model on a GPU, okay, and then do post-training quantization. So what happens is what is a model? Model is just basically a matrix of weights, which are float 32 kind of weights. Okay. So when they are in float 32, there's a very high likelihood that they are very sparse in nature. A lot of weights are very small in size. That's 0.00 some X number of things. So what you do in post-training quantization is that you convert this float 32 values to an integer 8 value. Right? And when you do that, it reduces the size, just like this banana, which has been shrunk out there when we are changing the pixel size, is that it becomes 1/4 the original size. And this is a beautiful way. Some models adopt to this very well, but other models, there is a loss in accuracy if you use only the post-training quantization method. And the other ones we'll talk about, so we'll discuss about, yes, Carl.
Yeah, so that last picture, why don't you go back to it? What is it doing? What is the AI doing? It's quantizing into the smaller squares?
Yes, so we are reducing the pixel size. Basically, we're taking 4 pixels, yes, and we are reducing it by 1. Okay, so instead of a 4 pixel representation, we use only a single pixel for representing those 4, right? And then we continue to doing that. So you have that shape in image, it still looks like a banana, but the size has reduced considerably.
Okay. So that helps. So it's a matter of trade-off between resolution and quantization, and then eventually the speed to make it do that. Is that what you're saying?
Correct. Yes, you got it right.
Pretty much. Yes. Okay, got it.
For most real world stuff, right? They'd like to go to smaller processors, faster, cheaper processors, lower power processors. So the 32 to 16 is a big price. 32 to 8 is a huge price drop, right?
Yeah, but it also introduces losses in that, which is called as quantization loss. We'll cover that.
Yeah, but the reason you would do that is because you are reasonably confident at what you're seeing, and you have just more other things to do with that information rather than just resolve the image, right?
You've left training. You've left the training mode, and now you're trying to go to production, right?
To insights, to bring bigger insights than the image.
Yeah. And the advantage of this post-training approach is that like data scientists are familiar with certain frameworks, right? And they want to use that because they're familiar with, understand its ins and outs. So you can use your framework. You want to use TensorFlow, you want to use Keras, you want to use PyTorch, use a framework, create a model, and then quantize it. So it's more of the ease of use or familiarity of use. Of course, you'll be doing testing and you'll see whether that final model fits your requirement or not. But yeah, so that's right. Yeah. So we'll look at other now during training. Also, we can implement these kind of optimization, and we look at 3 of them out here. The first is the weight pruning methods. So what happens out here is basically you are having layers and they are connected with each other. These are nodes and they are connected with each other. So you are removing out or cutting out some of those connections so that the matrix multiplication that takes place, because once you disconnect this, there's no multiplication taking place. And that considerably reduces the size. Okay. Now, this pruning, we do it during the training process. So when the model is there and it's training with the data, you cut off those nodes or those connectors, which you feel like, okay, they are not contributing to the final output. So the model tries to learn over it. Yeah, it adapts to those cuts. Like if you're a gardener, you'll understand that if you're cutting off some trees and pruning of those trees, it still learns on top of it. Like it grows around it. So we want the model to learn, but we also want to keep the size less. So we try to disconnect some of the connectors. So that is known as weight pruning. The second is called weight clustering. Now this is another interesting method. Is that what you do is you have those 16, you have a 4x4 matrix in your layers. Everything is a 32-bit float integer. You try to find centroids in it. For all these 16, you find some centroid index through a clustering algorithm. And you provide them as index. And then you assign those indices to these weight matrix. And so instead of storing this float 32, you're storing a 2-bit integer, which points to index value, which points to this index. And that again considerably reduces the size of your model. So you can use both these processes. You can use pruning, and then you can use weight clustering, and then you can use quantization. So using those 3 methods, it's likely that your model will reduce to 1/10 of its original size. Right?
Is there though a best practice or a recommendation on how large the training data set needs to be to use these techniques? Because
I'll come to the next slide talks about that very much. It talks about it because that is a very important point. The next 2-3 slides about we'll talk about it. This is a very important point that you have taken out, right? So yeah, this I wanted to make sure because I'm going to talk about quantization aware training out here. If you see this, this is your float value, number of values that a float integer will take compared to an int 8 integer, right? So if you can see that there is a loss, there's a lot of loss in once you quantize something. And there are rounding errors, there are computation errors which come up because you're multiplying int 8 values together instead of float 32. And all these keep accumulating. So this kind of adds to the errors out there. And this is very important when you're doing post-training quantization. You need to be aware of these factors. But if you introduce that during training, right? So that's called as a quantization aware training process. What you do is that you do the forward pass in float 32 integers, but the backward pass, when the weights are being stored, you store it as integer 8. So forward pass takes place in float 32, but backward pass takes place in int 8. And that's how you introduce something called as a quantization noise into the entire process. But because you are doing this during the training process, it makes it more robust. The model is more robust, the output, and the parameters have learned those quantization.
You know, Aakash, I just want to ask you a question. You know, I'm more familiar with video processing, where they quantize clusters. They do everything exactly what you said. The only difference is, of course, they have a known quantization method. And they do that in real time now in televisions, right? And a very large amount of it. They lower the bandwidth and then they expand it on the other end. So this is kind of similar, but more complex because there's this learning portion adds a lot of computation, is what you're saying. So now you got to pare it down a little bit, so you don't end up with so many damn calculations, basically. Is that right?
Right. So a lot of these things, when whatever you see in machine learning, computer vision, these come from this the field of video processing, and so we are taking a lot of fundamental stuff which has been there. Even in signal processing, a lot of things from signal processing is being used. A lot of things from vision, video processing, whatever, and we are using it out here. Something like NERF, which is like radiance fields that you create, right? You have a 3D object, it creates all those light which falls on it, creates optical illusions. A lot of material is there which we are trying to recreate using machine learning. So that is quite interesting, actually. We can have a separate topic on that. So before I go to this, so there's a optimization tools which I've listed out here. And some maybe you might find good for yourself, use it. Say TensorFlow Lite gives you the flexibility out there to convert multiple models to a more optimized sections, and you can use it to create models which can be deployed on your mobile app. And one good advantage of TensorFlow Lite out here is that they allow you to put a security code or encrypt your model. So if you're deploying it on the edge or on an Android machine, on an app, so you can encrypt the model and then save it. So that protects your IP out there. TensorFlow JS is just what I showed in what was shown in the demo. So we use TensorFlow JS. It basically, there are models. They have a model library where a lot of models have been trained, and we can use a Node.js kind of a framework to deploy and provide your inferences. DTCO is PyTorch based, and it's based on top of Detectron 2, which has been open sourced by Facebook Research. And they provide an entire framework where you can create faster models with more training. Yeah, and you can use it to deploy in a lot of interfaces. ONX is Open Neural Network Exchange, and it provides a kind of a flexibility that you can train in any kind of a framework and then optimize it to your requirement, may it be on IoT devices, microcontrollers, maybe a Jetson, a Raspberry Pi, or on a mobile device. And then there's Intel Distiller. This is more of a research project from Intel, and they don't really support it, but it also gives you all the algorithms that we had discussed earlier. They give those options, those APIs to do the distillation. And because it's from Intel, they have support for Intel edge devices out there. So here we look at what are the benefits of optimization. As we discussed, that there's always a balance between computational power, the speed, and what you can achieve out of that. So you need to maintain that balance whenever you're doing a deployment. Typical optimizations means that the size of the model reduces, and since the model size is less, the download bandwidth is less. Right? I have 15 MB model which have deployed on a browser. You require less bandwidth. Because the size is less, again, the inference speed is faster, there's lower latency, your memory usage is less, and correspondingly, your power consumption is also less. So all these are the optimization benefits, model optimization benefits, and there's privacy first, which I think is very important because you are doing inference, and this data is power basically. And if the data doesn't leave the client doesn't give out his power, and the data remains with the user. So no PII information is being transferred to central servers. That is very useful in IoT devices and health tech. A lot of like variables kind of place where you want the information to stay on the client side. Yeah. So this slide is when not to optimize. This is when you require high accuracy. This is actually where just like Lester asked a question is, what is the training data that you require? Now, if you have large amount of training data, that's when you can do use kind of model optimization training methods. If you have less training data, you cannot do that. Your models will not work with that type of kind of efficiency. So, so if you have less data, you need to use a proper the original models with their entire weights and everything. You have batch operations, you don't really require. If it's a batch operation that is taking place, you want to calculate recommendation engines, you want to understand transactional data, you can run it in a batch. Cost is, of course, not a factor for large companies. And yeah, if you accuracy is higher. So yeah, these are the 4 points that are the reasons when you not optimize the model.
I have a question for you that you're looking here at a vendor customer demarc, right? But even inside of a single corporation, there may be sensitivity about the data that the company may not want to make the full data set available to any employee or a random employee, so to speak. So are these techniques also being explored to preserve data confidentiality even inside of the corporation, to push the software push the code to the data as opposed to bringing the code to the developer?
Yes, yes. Yeah, so it's sort of like you want to maintain certain kind of a privacy standard, and you want to ensure those kind of walls are present so that people who are not authorized to see the data should not see it. But you want to also ensure that your customers get the best value for their they get to use your innovative products. And that's where something like a federated learning and all those concepts come into place. You create a framework which can then enable people to do the inference at the edge, let them learn things, but you're just creating the framework out there. And also that you maintain all your privacy standards, your health tech standards out there. So those are maintained out there. Cool. So Sean, just give me a sec. I would like to put up some links out here.
Okay.
Basically, it's my LinkedIn, my email ID, and
so that might be
it's my email ID.
So I put the email ID in the chat.
Okay, I'll just remove that then. So it's my LinkedIn. It's a link to the presentation. There's a link to the demo, and yeah, some fun stuff that we did at our company. Maybe so if you find that interesting, you could try that out.
I'll give folks a second or two to copy that if they care to. And
so Aakash, I've got, oh, sorry, Sean, I was talking over you.
No, go ahead.
Yeah, I've got one question. I've been all over the place here trying to kind of bring myself up to speed in machine learning. I did attend a webinar last week which talked about TinyML. So is TinyML the same idea, or the same? Is it a framework for doing machine learning at the edge? Is that the same thing, or is it something entirely different?
Yes. TinyML is a similar concept, which looks at deploying on IoT devices. I think there's a conference in June on TinyML. TinyML conference there.
Okay. Is that you say where is that taking place? Is that in person or virtual?
I won't know that. I'll have to check it. I just saw it a month back, so maybe I need to search for that.
Okay, great.
So they have a proper that kind of they work with universities also. So it's an organization which does that. So they work with universities and they provide grants also. So and they look for submissions on this. So.
It's end of March at the San Francisco airport. If you're talking about the Tiny ML Summit,
Yes.
I'll put that in the chat. Was there a different thing you're thinking about, Aakash?
No, I'm talking about that one. Yeah.
Oh, okay. Okay, thank you, Sean.
So there's a link there that you can register and, but it looks like it's on site. It's an on-site event. So, all right, gentlemen, I'm going to break here unless folks have any final questions. And I want to thank Aakash very much for a fantastic and very thought-provoking talk. This was quite quite interesting.
Yes, Aakash, that was great. Thank you very much.
Thank you.
Thank you. Thank you.
Thank you. See you all later.
See you.